In this video, we are going to learn Stokes Theorem, which connects the concepts of line integrals and surface integrals together. Before we get to the statement of Stokes Theorem, we first need to have a discussion about orientation. Now separately, when evaluating the line integral of a vector field, we determine the orientation of the curve based on phrases like clockwise or counterclockwise. And when evaluating the surface integral of a vector field, or a flux integral, we determine the orientation of the surface with phrases like upward or outward. Since we're connecting these ideas, we need a way to decide if the orientation of a curve agrees with the orientation of a surface. And that's where we start. So let C be the boundary curve of an oriented surface S. The boundary curve C is said to have a positive orientation if it is traversed so that the interior of the surface S lies to the left of the curve. The boundary curve C can also be expressed in terms of S with that partial notation as we see here. This is nice because it emphasizes the fact that the curve is the boundary of the surface and the ideas are connected. So let's draw a picture to get a sense of what this is describing for us. Okay, so we have our three-dimensional axes, X, Y, and Z. We're going to draw a simple surface with a boundary curve. So we can draw the surface to look like this. So there's our surface S. The boundary curve goes along the edge or the opening. So in red, we'll highlight the boundary curve. So that's C. Or we can write it in terms of S. Okay, so now we need to bring orientation in. So we're starting with an oriented surface. So the surface we drew needs an orientation. We can decide upward or downward. For simplicity, let's define the orientation upward. So there is our unit normal vector that is orienting the surface for us. So really what we're doing is defining what we can think of as the positive side of the surface. That's the side that we want to keep on our left when we're traversing the boundary curve. So if that's the case, then we want to move along the boundary curve in this direction, which we would say is the counterclockwise direction if we were looking straight down at the surface. So now that we have the orientation of the surface and the boundary curve, how are we supposed to tell if they agree or not? And something we've used in the past, the right-hand rule, is really effective here. So this means that orientation follows the right-hand rule. Right? So checking if the orientation agrees, we're really checking if the right-hand rule is true. So start by facing the palm of your right hand toward the interior of the surface. Curl your fingers in the direction of travel around the boundary curve C, so go in that counterclockwise direction. Your thumb should point in the direction of the normal vector to the surface, so in this case your thumb should point straight up. And that is how we can check that the orientation of the surface and the boundary curve agree. Now typically in a Stokes theorem problem, we're going to be given one orientation of either the surface or the boundary curve, and we can use the right-hand rule to figure out the orientation of the other piece. Another way to visualize it is to place yourself on the boundary curve. If your head goes in the direction of the normal vector to the surface, then you should walk around the boundary curve keeping the positive side of the surface on your left-hand side. Okay, so that's another good way to visualize the orientation. So now that we have that defined, let's get to Stokes theorem. So Stokes theorem states, if we let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C with positive orientation, so take the diagram on the last slide as a good example of all of that. Let the vector field f of x, y, z have components with continuous partial derivatives on an open region in 3 space that contains S. So it contains the surface. Then Stokes theorem says that the integral along C of f dot dr is equal to the double integral over S of curl of f dot ds. So we've equated a line integral on the left side to a surface integral on the right side. On the left side, we're going along the boundary curve C, and we're looking at how the vector field moves, F. On the right side, we're looking at the flux of the curl vector field, which essentially is going to tell us how the vector field is moving over or along the surface. And those two things are equal. Now from a mathematical point of view, the reason this works is because curl is like a derivative of a vector field, we're integrating a derivative operation, which brings back the fundamental theorem of calculus. Integral of a derivative leaves us with the original function, which in this case is the vector field f. Single integral of f turns it into a line integral, which we see on the left side. Now, putting some words here, Stokes' theorem states that the surface integral of the curl of a vector field f over a surface S, so that's the right side, is equal to the circulation of the vector field f along the boundary curve of the surface. So instead of thinking about the line integral representing work, which is typically what we thought of when we see f.dr, we're going to think about it as circulation, which is saying how the vector field is moving along the boundary curve. Let's go a little bit deeper to get a sense of what this is showing us, and then we'll get to our problem solving. So an informal look at why Stokes' theorem works. If we recall that the curl of a vector field measures how much the field is rotating or swirling around a point, we can think of this rotation as a form of circulation. Okay, so if we recall, curl gives us a vector at every point. That vector represents the axes of rotation for that particular point, and what that's telling us is how the vector field is rotating around that particular point. And we can do that for all the points in the vector field. And that we can think of as the idea of circulation. So then Stokes' theorem states that if you sum up all these infinitesimally small circulations around every point on a surface S, it's equivalent to finding the total circulation of the vector field around the boundary curve C that encloses the surface. Now, to make a little bit more sense of this statement, let's draw another picture. So we'll draw a different surface. Okay, so we have a surface in space here. Okay, and then there's some sort of vector field going on here. And what we're going to do is we're going to break up this surface into a bunch of small regions. Now again, picture these to be infinitesimally small regions. We're making them big enough to draw a diagram. Now, imagine there being a single point in each of these infinitesimally small regions. We can compute the curl of the vector field at each of those points. And what that's going to give us is axes of rotation, and we can figure out how the vector field is rotating or circulating around that particular point. So what we're going to do is we're going to draw circulation around each point in these regions. So for simplicity, let's just go in the counterclockwise direction. So we've computed curl for each of these points, and what that told us is that the vector field is rotating in the counterclockwise direction around each of these 8 points in these infinitesimally small regions. Okay, so somehow we have to show that this is equivalent, like summing all of these up is equivalent to just looking at the vector field around the boundary curve. Well, let's highlight an adjacent side of 2 infinitesimally small regions. Well, in the top region, that counterclockwise circulation is going to go from left to right along that little edge of the region. But right below it, that counterclockwise rotation below it is going to go from right to left. And what we're going to get along this edge that we've highlighted in blue is a cancellation of circulation. And we can repeat the process for any piece of the surface that is adjacent, right? Any of these adjacent little pieces. Except when we get to the pieces that are on the boundary curve. So I'll highlight the boundary curve in red again. Okay, so that's C. Along the boundary curve, right, so if we look right here, the circulation is going counterclockwise. So for that piece that's on the boundary curve, we're going from left to right. Now there's nothing below it that's going to cancel out. There's no circulation below it that's canceling out. So this circulation counts as we sum up all of our circulation, right? Along the blue, it wound up canceling out the circulation from above and below. Yet along the boundary, we have to count that circulation because there's no cancellation. And that's going to happen for all of these pieces that wind up on the boundary of the surface. We wind up putting together all those pieces. We create the boundary curve. And then we're really just looking at how the vector field is moving along that boundary curve. Right? So that's a little bit of the theory behind Stokes' theorem. We can go much deeper, but I think this gives us a good sense of how Stokes' theorem works. Now, another connection to make is the fact that Stokes' theorem is really just the equivalent of Green's theorem if the surface was on the xy plane. So Stokes' theorem allows us to extend Green's theorem into 3 space. Right? If we were to take the vector field, or a vector field, in 2 space, so create a vector field, call it P, Q, and 0, that would keep us on the xy plane. Normal vector to any surface on the xy plane is going to be just k. So really, Stokes' theorem says that line integral of f dot dr is equal to the double integral of s of curl of f dot ds, which we can write as double integral of the curl of f dot k dA over the region in the xy plane. And if we did this computation out, really what you'd see is that dot product is nothing more than partial of q with respect to x minus partial of p with respect to y, which is the statement of Green's theorem. Okay, so it's a nice connection to make that Stokes and Green's theorem have this relation to one another. So now that we've stated the theorem, we've got all that set up, let's get to our problem solving. So the first thing we're going to do is verify Stokes' theorem, which means we're going to do both sides of the theorem and see that we get the same answer. So the vector field they've given us is negative y xz. The surface S is the part of the paraboloid z equals 5 minus x squared minus y squared that lies above the plane z equals 1, oriented upward. So they've given us the orientation of the surface, and we'll have to use that to find the orientation of the boundary curve. Now, since they oriented the surface for us, let's start with the surface integral side of Stokes. So we're going to start by evaluating the double integral over the surface S of the curl vector field of f dot ds. Okay, in these examples, if we can draw a picture, especially when we're trying to figure out what is the surface, what is the boundary curve, it's always going to be helpful. So here we'll draw a paraboloid that opens down. I'm not going to go all the way to the xy plane because we're cutting it with the plane z equals 1. Right, so we have our paraboloid, we have our plane. So the paraboloid is the surface that we're focused on. Boundary curve is the opening of the paraboloid cut by that plane z equals 1. Upward orientation, so the normal vector to the surface points up. And might as well use the right-hand rule here. We don't need the boundary curve yet. We'll do that in the second part. But if our thumb points up and we curl our fingers, that means we're curling our fingers in the counterclockwise direction. So our movement along the boundary curve is going to look like that. Okay, so for the surface integral, first thing we need to do is find the curl of f. Okay, so computing curl, we set up our matrix, partial with respect to x, y, and z, negative y, x, and z. Now if we go through the procedure of finding that cross product, we're going to get 0, 0, 2. I'm not going to walk us through that. I think we've practiced this enough, and I would encourage you to try this on your own and see that you get 0, 0, 2. Next thing we need is that normal vector that orients the surface. Okay, so our surface is z equals 5 minus x squared minus y squared. That's the surface that we're focused on. So since we can use a trivial parameterization, well then let's just define the function g of xyz to be x squared plus y squared plus z minus 5. And then the gradient of g, which is 2x, 2y, and 1, will be our normal vector. Now we need to check the orientation. So look at the z component. It's positive. So that means it's an upward vector, which is the orientation we need. So then we're going to dot the curl with that normal vector. So we get the double integral of just 2 dA over the region D. Now that region D is the intersection of the plane and the paraboloid. So what that's going to look like, if we do 1 equals 5 minus x squared minus y squared, is x squared plus y squared equals 4. So circle of radius 2. So this is really nothing more than 2 times the area of that circle. So 2 times 4 pi, which is 8 pi. Okay, so the value of the surface integral side of the curl vector field, which is representative of the flux of the curl vector field through the surface, is 8 pi. Now to verify, we need to do the other side of the theorem and see that we get 8 pi as well. Okay, so same setup. I'll just quickly redraw our diagram, but now we're going to focus on the boundary curve as opposed to the surface. So we have the same diagram. You don't need to redraw it necessarily. Okay, so normal is going up. Go along the boundary curve with the right hand rule. Means we're going counterclockwise. Okay, so now we're evaluating a line integral. So we need to bring back all of the skills in doing so. Okay, so the boundary, that's going to be in the plane z equals 1. And if we're in the plane z equals 1, the circle is x squared plus y squared equals 4. And we're going to combine all of these pieces to parameterize that boundary curve. So c gets parameterized as r of t equaling to 2 cos t, 2 sine t, 1. Right? And we're moving counterclockwise, right, from the positive x to the positive y axes. And feel free to draw this in the xy plane if that's helpful and put the arrows in. So our parameterization is good. It's going to go from 0 to 2 pi. Then we find r prime of t, which is negative 2 sine t, 2 cos t, 0. Redefine our vector field in terms of t. So that's going to be negative 2 sine t, 2 cos t, 1. And then we're setting up our integral from 0 to 2 pi, dotting r prime with the vector field f. So that's going to be 4 sine squared t plus 4 cosine squared t dt. So that's the integral from 0 to 2 pi of 4 dt, which is going to be 4 times 2 pi, which is 8 pi. So that verifies Stokes theorem because we got the same value on both sides. I like this example because we didn't really focus on any integration. We focused more on the setup of both sides of Stokes theorem. Now, for most problems, we're only going to have to do one of these parts. So we'll either be asked to evaluate the line integral, and instead we will evaluate the surface integral, or vice versa. And typically what they're trying to tell us is that it's easier to do the other side of the theorem. So an example that looks like that, use Stokes theorem to evaluate the line integral of f dot dr, where the vector field is 2z y x squared, and c is the boundary of the plane x plus y plus 2z equals 2, oriented counterclockwise when viewed from above. So, could we possibly do this directly? Maybe, but by being told to use Stokes theorem, it's an indication that it's probably easier to evaluate a surface integral here. So let's start by just drawing this region. Maybe that will give us some insight as to why. So we'd have 2 on the x, 2 on the y, 1 on the z for our intercepts. So there would be the curve, right? So I'll highlight it in red just to stay consistent. So basically we have a plane, and we're going along these 3 edges, counterclockwise when viewed from above, so that's going to go in that direction. So if we wanted to do a line integral here, we'd have to do 3 of them along each edge. So that's where a surface integral might be simpler because we only have to do 1 of them. There's only 1 surface bound by these 3 curves. Okay, so we really are focused on then the surface integral of the curl vector field. Okay, so we have a few pieces that we're going to need. First thing we need is the curl. Okay, so the curl of this vector field, I, j, and k, partial with respect to x, y, and z. So we have 2z, y, x squared. So we're going to get 0, negative 2x plus 2, and 0. And if you go through the process, that's the curl vector field you should find. Next, we need the surface, because from the surface, that's going to give us the normal vector. So the surface that goes inside of these three boundary curves is that plane that was defined for us. Okay, so the surface is the plane. So we could solve this explicitly for z. So z equals 2 minus x minus y over 2. And the reason that's helpful is we could use a trivial parameterization, or instead we can just set up that function g. So g of x, y, z. Move everything to one side. So we'll go x over 2 plus y over 2 plus z minus 1. Then we're going to find the gradient of g, which is 1/2, 1/2, 1. Now, is that oriented the right way? Well, let's go back to our diagram, use the right-hand rule. So if we curl our fingers counterclockwise, our thumb is going to point up off of the surface. So our normal vector would look like that. So positive x, positive y, positive z looks to check out and match the direction that the normal vector should be going in. So we're good there. So now we're going to take the double integral. Let's go back to black here. So double integral, dotting the curl with that normal vector just gives us negative x plus 1. And then we have to set up the bounds of integration. So in the xy plane, since we're using a trivial parameterization, everything in terms of x and y, it's going to be that little triangular region, 2 and 2, so y equals 2 minus x. We can treat this as type 1 or type 2. Let's go type 1, so that means we're going dy dx here. So y goes from 0 to 2 minus x. X goes from 0 to 2. Not going to focus on the integration here. If you do out the integration, you're going to get 2/3 as the value of this integral. Okay, but this was an example where we were asked to evaluate a line integral, but we used Stokes to turn it into a surface integral that was easier for us to compute. Right? Way easier than doing 3 separate line integrals. Now going in the other direction, evaluate the surface integral of the curl vector field, where the vector field is y, negative x e to the z, x e to the y, and s is the portion of the plane y equals z inside the cylinder x squared plus z squared rather equals 1 with downward orientation. So this is telling us it's probably going to be easier to evaluate the line integral instead. So first thing, draw our region, so x, y, and z. So we have the cylinder going along the y-axis. Okay, so there's our cylinder. Then we have y equals z, which is going to look like this. Okay, so the intersection of those two going to create the boundary curve. And that's important for us because that's what we're focused on. Now the surface is the plane, right? So the surface is that part of the plane inside. Downward orientation means our normal vector is pointing down this way. So if we use the right-hand rule, that means we are going to be moving clockwise around our boundary curve. Okay, so something we have to consider. All right, so first thing we need to do is determine the boundary curve, or parameterize the boundary curve. So we have y equals z and x squared plus z squared equals 1 as the two equations that are going to define this boundary curve, right? It's the intersection of these two surfaces. So then parameterizing x and z would have to be cos t and sin t because x squared plus z squared equals 1. So we have cos t and then we have sin t. And then y equals z, so that would be sin t. Now this parameterization right here moves in the counterclockwise direction. So we have two choices. We either leave it alone and negate our line integral, or we can adjust the parameterization so that it moves in the counterclockwise, in the clockwise direction rather. So if we make the adjustment, we would negate the sign part there. If you'd rather leave it alone and negate your line integral, that's fine too. Just don't forget to negate your line integral. So we have r prime of t equals negative sine t, negative cosine t, negative cosine t. We need to redefine our vector field in terms of t. So that's going to be negative sine t, negative cosine t, e to the negative sine t, and then cosine t, e to the negative sine t. So then we have the integral from 0 to 2 pi of our dot product. So that's going to be sine squared t plus cos squared t, e to the negative sine t, minus cos squared t, e to the negative sine t dt, which is really just the integral from 0 to 2 pi of sine squared t dt, which if you do this out, you're going to get pi. And this is a great example to practice integrating sine squared. But again, we see Stokes' theorem at play. Now, the last thing we need to talk about is when we're looking at a boundary curve and going to a surface integral, do we always have to use the surface they give us? So if two oriented surfaces, S1 and S2, have the same positively oriented boundary curve C, then that surface integral of the curl vector field is going to be equivalent for both surfaces. Okay, so this is a really important result. What it means is take any two surfaces that have the same boundary curve, the surface integral of their curl vector field is going to be equal. Now, for Stokes' theorem, when we're trying to evaluate the line integral along a closed curve, any surface that has the curve as its boundary can be used. So the idea here is pick the easiest. And we can use this result to show that if we have a closed surface, so think of a sphere, that the surface integral of the curl vector field is just going to be 0. And you can do this in a number of ways. Just a simple way to think through this is if you have a closed surface, you have no boundary curve, so then there's no movement of the vector field along the boundary curve since it doesn't exist, and therefore the value of this integral is 0. Okay, so let's look at one last example using this fact. So use Stokes' theorem to evaluate the line integral of f dot dr, where the vector field is 2y e to the y squared plus z, z e to the xy. C is the intersection of the cone, z equals square root of x squared plus y squared, and the sphere, x squared plus y squared plus z squared equals 2, oriented counterclockwise when viewed from above. Okay, so if we're using Stokes, that means we're going to a surface integral instead. And really the focus of this particular problem is on the surface itself. So we have x, y, and z. So we have a sphere of radius rad 2. We only have to focus on the top half because the cone is up here. There's the intersection of the two. So there is the boundary counterclockwise, so we're moving in this direction along C. So now the question is, what surface do we want to use for the surface integral? So we have some choices. Inside of this boundary curve is definitely part of the sphere, right up here. Okay, so part of the sphere is inside, so we could use that. Now I'll erase that. We can use the cone, right? The cone is a surface that definitely has that boundary curve. But both of those, it would be less than desirable to find the normal vector. Instead, if we realize, we can just put a plane, right? So we can take a plane, and part of the plane would fit perfectly right inside that boundary curve. And the plane is definitely the simplest surface that we can pick, so that's the one that we want to choose here. And that's going to make the computation the simplest. Okay, so in order to find the equation of this plane, we need to find the intersection of the two surfaces. And really we want it in terms of z. So really x squared plus y squared is z squared from the cone. So going into the equation of the sphere, we'd have z squared plus z squared equals 2, which means that 2z squared equals 2, z squared equals 1, z equals 1, because we're only focused on the positive one. Okay, so we have z equals 1 as the equation of the plane. With the right-hand rule, the normal vector is going to point upwards. And maybe I'll highlight that in purple just to give us a different color there. Okay, so our surface is z equals 1, so we could say that g of x, y, z equals z minus 1. Gradient of g is 0, 0, 1. We also need the curl vector field. Okay, so I'm just going to write this out without the setup. So that's going to be xz e to the xy minus e to the y squared plus z. Negative yz e to the xy and negative 2. Right, the focus here is more on the surface. You should be able to set that up. So we have the double integral. Dot these two together. We get negative 2 dA over the region. Now what region are we integrating over? Well, it's that circular region inside of the boundary curve, which is going to be the circle of radius 1. Right? Z equals 1. So we would have x squared plus y squared equals 1. So this is really negative 2 times the area of that region, which is pi. So negative 2 pi is our value. And really here, we use the fact that we could pick a simpler surface to make the surface integral easier for us. Okay, there were a few options, but the plane was the easiest. So this is Stokes' theorem. Practice. Because we are doing both line integrals and surface integrals here, it's important that we're comfortable on both sides because it's useful in both directions. And with that, I'll see you in the next video.